Welcome to part 2 of lecture 7, integrate surface area and volume. We'll be looking at both volume and surface integrals, the simplest ones that we can, primarily three-dimensional integrals, although the surface areas are 2D integrals in 3D. So let's start with volume, and I think it's really important to start right from the beginning and ask, what is the definition of volume? How do I compute volume? I find most people actually don't remember this. Even though it's taught in nearly every calculus textbook. It's the ratio of the amount of stuff in an object relative to the amount of stuff in a unit cube. So my unit cube is my measure by which I'm going to measure all volumes with respect to. So the unit cube always has volume 1, and then I have to determine what the volume is relative to that unit cube. We typically work with three different coordinate systems in 3 dimensions. Cubic coordinates, which you're most familiar with, x, y, and z. Cylindrical coordinates, which we use coordinates rho, phi, and z. That's essentially polar coordinates plus a vertical direction labeled by z. Sometimes you'll see it's labeled r theta z or even r phi z. All of those are equally possible, but I'm going to try and use rho phi z, at least for this lecture, so that we don't confuse it with the spherical coordinates. The spherical coordinates are given by r theta and phi, and I'm assuming that you remember exactly how theta is constructed and how phi is constructed for spherical coordinates. If you don't, real good opportunity to go get out something like a Khan Academy and remind yourself about what spherical coordinates are. What I will focus on very carefully is what the volume element is. So in cubic coordinates, if you look down here, we have a cube. And what are the sides of the cube? Well, one side is dx, one side is dy, and one side is dz. So the volume of that cube is going to be dx times dy times dz, and that means the volume element is dx, dy, dz. That's relatively simple. Everyone has no problem at all understanding that that's the volume element in 3D for a cubic system. Now let's go to cylindrical coordinates. Drawn for you in the middle is what one of these small little boxes is. The height is easy, that's dz. The length along the radial direction, also simple, that's d rho. The thing that you have to think about for a second is what is the length along the angular direction. If I move an angle d phi, my length is going to be rho, the radius, times d phi. Remember, that's the way that we determine arc length of a circle, or if you like, that's the way radians are defined. So one length is rho d phi, one is d rho, one is dz. I multiply all of them together, and then it's conventional to associate the rho with the d rho, because that's where it will appear when we're doing the integrals. So I write it as rho d phi dz. Okay? Not too hard, very similar to what you would get for polar coordinates, which most people are familiar with, that you get an r dr d theta is typically the way that it's discussed. Now on to spherical coordinates. Spherical coordinates a little bit more complicated, but really not so bad. We look at the little volume element that is highlighted in the center part of the figure, and the width coming out in the radial direction is, of course, dr. Then we have to determine what is the length along the great circle that's going through the ZR plane with a line going through it, and we're moving an angle d theta, and we're at a radius r, so that length is going to just be r times theta. And then finally I need the direction in the d phi direction. I need the length there. I'm moving an angle d phi, but I have to determine what is the radius over which I'm moving that. It turns out that's the projection onto the xy plane of r, so it ends up being an r sine theta times d phi. And so now when we put all of that together, and once again we associate all the r factors with r and all the theta factors with theta, even though they didn't come from the dr or the d theta parts, we get r squared dr sine theta d phi. That's the form that most of you have probably seen it. It turns out it's actually much more convenient in many cases when we're doing integrals to think about this in terms of the inverse of the chain rule and convert sine theta d theta into d cos theta. Of course, I can just take the differential of d cos theta. I get sine theta d theta. You might be worried about the minus sign. it turns out the volume measure has to always be positive, and if you take that into account, then the fact that I'm going from integral limits that were 0 to pi for theta into integral limits that go from -1 to 1 for d cosine theta, because cosine pi is -1 and cosine 0 is 1. You see I've actually inverted the order of those integration variables, which is how the minus sign disappears. And the bottom line is you don't have to worry about the minus sign when you're doing these kinds of differentials. So we can convert sine theta d theta into d cosine theta, and you'll see me do that a lot in this class. All right, let's look at an application. We want to find the volume of the sphere. Well, it's most useful to use spherical coordinates because the equation of a sphere is just r is less than or equal to a, with a being the radius. So to get the volume, what we have to do is an integral, and I'm essentially going to integrate the volume element over the sphere. Well, how is the sphere defined? It's the region where r goes from 0 to a, so you can see those limits on the left-hand side. And then it's just the volume element integrated over all of the angles because the sphere is present in all possible directions. So I get an integral dr r squared, integral -1 to 1 d cosine theta, integral 0 to 2 pi d phi. I can now do that integral over phi very simply. It's going to give me 2 pi, and I'm left with the other two terms for the integral. I can now do the integral over d cosine theta. It's just equal to 2. This is one of the reasons why converting it to d cosine theta rather than having a sine theta d theta comes inconvenient. That gives me an overall factor of 4 pi. I have the integral over r still to do, but the integral of r squared is just r cubed over 3, and I can see I have left out a 1 over 3 there. I will correct that for you. The correct answer there is 4 pi over 3a cubed. That's simply a typo. And of course, that is what the volume of a sphere is. Let's move on to looking at the volume of a cylinder. I'm reminding you about what those differential elements are. The cylindrical coordinates are useful here because the equation of a cylinder is simply rho is less than or equal to a, and 0 is less than or equal to z less than or equal to h. So we once again integrate the volume over that volume element. The rho goes from 0 to a, the phi goes from 0 to 2 pi, and the z goes from 0 to h. The integral over z is easy to do. I just get h. The integral over phi is easy to do. I just get 2 pi. And then the integral over rho is going to be rho squared over 2. The 2 in the denominator and the 2 in the numerator cancel, and that gets evaluated to an a squared, and I get pi a squared times, once again that's a typo, I'm sorry, pi a squared times h is what that is supposed to be. And of course that's what the volume of a cylinder is. It is simply the area of the circle, pi a squared, multiplied by the height, which is h. So the volume of a cylinder would be pi a squared h. So let's now look at surface area. For surface area, I have to do the surface area of the two circular end caps and then the surface area of the height of the cylinder itself. And so there are two different pieces I have to add together. Now there are two circular end caps, so I get a 2 in front of that one. The radius is going from 0 to a, the angles are going from 0 to 2 pi, and z is a constant here, so there's no integral over z because it's a two-dimensional integral because I'm just integrating an area. And then the area for the sleeve that goes around in the horizontal direction, that has an integration from 0 to 2 pi. It is rho d phi is the integration element, but rho is equal to a for that part of the cylinder, so I can replace rho by a. And then I have an integral from 0 to h of dz. Now let's evaluate the angular integral for the first part, and I will get a 4 pi integral 0 to a d rho times rho. And I'll evaluate the z integral for the second part. I'll get an ah integral 0 to 2 pi d phi. Those integrals that are left are easy to do. The integral over rho is going to give me an a squared over 2, so I get 2 pi a squared. And the integral over phi is going to just give me a 2 pi, so I get 2 pi ah. And indeed, that's what the surface area is. Each spherical end cap is pi a squared. There are two of them, so I get 2 pi a squared. And then the perimeter of the circle is 2 pi a. I have to multiply that by h. It's a nice rectangle if I unroll the cylinder, and that gives me the rest of the surface area. What about the surface area of a sphere? Well, once again, the surface of a sphere is defined by r equals a, and I'm going to be just integrating an area. So I set r equal to a, that pulls that a squared out of the integral, and then I just have an integral over the angular coordinates. Integral -1 to 1 d cosine theta, integral 0 to 2 pi d phi. And I can do the integral over d phi, it just gives me a 2 pi. I can do the integral over d cosine theta, that gives me a 2. And I'm left with 4 pi a squared, which indeed is the surface area of a radius. And fortunately, I have no typos in the formulas that I'm using here. Okay, to generalize this, one situation that's often looked at are surfaces of revolution. And I've sketched for you here some function y of x that's revolved around the y-axis. And we might be asked to calculate either the volume or the surface area of that. So the surface of revolution just revolves y of x around the y-axis. And so the radius for each height y is just equal to x. And to get the volume, we compute it by adding up the disks that have a height dy. And we add those up. For the surface area, we do that by finding the perimeter of the relevant circle, which is 2 pi x, and we multiply it by the arc length in the vertical direction, because it's not exactly in the vertical direction. It'll go somewhat in the y direction, somewhat in the x direction. So I have to multiply it by our old friend ds. So if I put that together, I'm going to get the following integrals. Of course, you're going to have some examples of this on the homework. For the volume, I'll have an integral from y min to y max dy of pi x squared. We typically want to integrate with respect to x instead of y, so I use the inverse chain rule to convert that to an integral over x. I can pull the pi out, and I get an integral from x min to x max dx dy dx times x squared. Similarly, if I want the surface area, I have an integral from the beginning of the surface to the maximum length of the surface, ds, times 2 pi x, x being a function of s in this case. Now I'm going to use the inverse chain rule to convert from an integral over s to an integral over x. So the 2 pi comes out. I get 2 pi integral from x min to x max dx. Our old friend ds, which has this extra factor, square root of 1 plus dy by dx quantity squared. And then I have to multiply by that radius, which is x. And so that then becomes the formula for the surface area. So you'll have a chance to explore these kinds of integrals on the homework, and I hope that this has clarified something that you might have found a bit difficult in looking at volumes and surface areas. We're going to focus in class on looking at things where the mass density, if I think about calculating a total mass, may not be a constant, because that's really what integration is for, is evaluating situations where things can change as the integrations and the coordinates change. You usually work with things that have constant mass densities, but there's lots of things out there that don't, and being able to handle those kinds of complications is very important.